Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. I welcome you to the 24th lecture for the series of lectures on advanced computer architecture. Today, we will be having a concluding discussion on the instruction level parallelism. After a brief review of what we discussed last time regarding software techniques and hardware supports for enhancement of instruction level parallelism, I'll give you a few examples to preserve exceptions, and then we will continue our discussion for compile time hardware support for the memory reference speculations. Then at the end, I'll give you a brief summary of highlighting the difference and merits and demerits of speculation mechanisms, which is hardware versus software discussion which we have made so far. So last time we discussed the methods to provide hardware support for exposing more and more instruction level parallelism at the compile time. We introduced the concept of extension in the instruction set architecture by including the conditional or predicative instructions. We found that such instructions can be used to eliminate branches or to convert the control dependence to the data dependence, which is relatively simple to handle. Thus, it improves the overall processing performance of the system. We also introduced the hardware and software-based abilities required to move the speculated instructions before the branch condition evaluation while preserving the exception behavior. We further introduced 4 different techniques to support speculation and to move instructions such that the mispredicted speculative sequence is not used in the final execution, but the exception behavior is preserved to take care of the exceptions that may be used later. However, in order to study these methods, we distinguished between the exceptions that indicate the program errors which normally cause termination or the program errors which resume normally. The typical examples of the behavioral exceptions that indicate the program error and terminate is the memory protection violation. In this case, the result of the program that gets such an exception is not well defined. Therefore, if such an exception arises in speculated instructions, we cannot take the exception. Hence, we need to preserve such an instruction for later use. The example of the behavioral exception that indicate the program error which could normally be handled and the program normally resumes is the page fault in the virtual memory. Such exceptions are preserved and processed for speculative instructions as if they were normal instructions when instruction is no longer speculative. Now, with this much discussion from our previous review, let us study in details the methods to preserve the exceptions. Last time, I pointed out 4 different methods which are introduced. These methods are the fast mode approach, the speculative instruction method, the poison bit register method, and hardware buffering technique. I will take up these methods one by one with some typical examples and explain to you how these methods are used. For this, let us first of all talk about the fast mode operation. The simplest approach to preserve exception is one where hardware works cooperatively with the operating system, and it handles presumable exceptions under the program control. This approach is normally referred to as the fast mode operation for preserving the exception. Here, the hardware and software preserves the exception behavior for the correct program, but it ignores the exception behavior for the incorrect program. However, before I go in details, let me explain what do we mean by a correct program and an incorrect program. A program may be defined as a correct program if the instruction generating the terminating exception is speculative and the speculative result is simply unused. That is, the speculative instruction returns a value that is not harmful for the program. Whereas an incorrect program is one which previously have received a terminating exception and will get an incorrect result in the present instruction. Thus, the exception behavior is mispredicted. Hence, the exception behavior as a result of speculated instruction will not be used in the final computation if mispredicted. So now let us consider a typical example of code fragment for if-then-else statement of the form as shown over here. Here you can see that this if-then-else statement says that if A is equal to 0, then replace the value of A by the value of B. Whereas if A is not equal to 0, then replace the value of A by A plus 4. Now, here in this case, we will see how this code can be modified to preserve the exception behavior. Here, if we assume that A is available at the memory location specified by the contents of register R3 and B is available at the memory location specified by the contents of register R2, then the code based on the speculation that the then clause is almost always executed can be written in the form shown over here. Here you can see that the then clause starts from the load instruction, which loads the value from the memory location R2 into the register R1. And for the else clause, a number 4 is added to the present value of A. So, as you can see from here, from this example code, the second instruction, that is the branch instruction, shows that here we speculate that then clause is almost always executed. That is, the program will rarely branch to the else clause. Therefore, the second load instruction, where the value b at location specified by the contents of register R2 must be preserved. So from here we can see that in order to preserve the speculation, we use a temporary register. Say, let us use the register R14, which is suppose presently unused, and this register is to be used to avoid destroying the contents of R1 when B is being loaded as in initial code. So the revised code can be seen from here. Here you can see that we have moved the branch instruction to the third instruction slot, whereas the speculative load is in fact one where the value at the location R2, which is corresponding to the value of B, is being preserved, and it is speculatively loaded into the register R14 for later use. Here is a new code that preserves the speculation in a temporary register R14 to avoid destroying R1 when B is loaded. Here you can see that the second load instruction is corresponding to the speculative value of B at location given by the contents of register R2, and this value is preserved in the temporary register R14 to be used in the then class. So this method basically shows that here we are using a temporary register to preserve the value which is speculated in the beginning, and this will in fact implement the fast mode operation for the speculative instructions. The second method, which we mentioned in the beginning to deal with the exception behavior preservation, is known as the speculative instruction use. This approach basically introduces speculative version of instructions. The two new instructions are introduced known as the speculative load, usually written as SLD for the MIPS architecture, and speculative check, written as SPEC, stands for speculative, and CK stands for check, that is spec check is the speculative check instruction. These instructions are used to preserve exception behavior exactly rather than speculatively. Here these instructions do not generate terminating exception. Rather, these instructions check for such exception. The combined use of these two are similarly some more speculative instructions to preserve the exception behavior exactly. Now let us see this thing with the help of our previous example, which we will reconsider over here to explain the use of additional speculative instructions as discussed over here. Here we assume that the temporary register R14 is still available, and we can use this as and when needed. For this, let us look into this revised code which has been written by using the speculative instructions. Here you can see that the second load is a speculative load. Here the load instruction speculates in respect of the branch instruction whether it will be taken or not taken. In this example, we are assuming not taken. The speculative check requires to maintain a basic block for then clause, thus it preserves the exception behavior. Notice here that extra code is required to check for possible exception. Thus, this shows that here is some extra overhead. And this checking operation is performed by the fourth instruction here, which checks if the speculation is correct or not. That is, whether the branch has been taken or otherwise. So this example, therefore, shows that with some extra overhead, we can preserve the exceptions. Now let us consider the third technique to preserve exceptions, and this third technique is known as the poison bit approach. The basic concept behind this poison bit approach is that the speculative movement of instructions must not cause exceptions. This speculative movement may be before branch or before reordering of load or store operation. If an exceptional condition occurs during a speculative operation, then the exception is not raised. Here, a set of bits called poison bits is attached to every instruction and to every result register to indicate whether the instruction is speculative or not. These poison bits used to track exceptions as they occur, but they postpone any terminating exception until value is actually used. So the speculative bits are simply propagated by speculative instructions. When a bit is set in the result register, it indicates that an exception condition has occurred. When non-speculative operation encounters a register with speculative bit being set earlier, an exception is raised. The poison bits cause a fault when a normal instruction attempts to use the register. Now let us see what is the sequence in which different steps are to be performed to preserve exception by using poison bits. For this purpose, the first step is that the poison bit of the destination register is set whenever a speculative instruction results in terminating exception. Secondly, all other exceptions are handled immediately. The third step is that if the speculative instruction uses a register with poison bit turned on, then the destination register of the instruction simply has its poison bit turned on. Whereas if the normal instruction attempts to use a register source with poison bit turned on, then the instruction causes a fault. Thus, any program would have generated an exception still generates one, although at the first instance where a result is used by an instruction that is not speculative. Furthermore, the stores are never speculative as the poison bits exist on registers only. Therefore, only the loads are speculative and stores are not speculative. Now, let us reconsider our earlier example of if-then-else statement and see how it would be compiled with speculative instruction such as sload and register R14 with poison bit available here, and also to show where an exception for the speculative memory reference will be recognized. For this, you can see over here that for the if A is equal to 0, then A is equal to B, else A is equal to A plus 4 statement. Here we assume that A is set at location identified by the contents of register R3 and B is specified by the contents of the location specified by the register R2, and that R14 is unused, and we are assuming that it is available for this code. For this purpose, you can see here onto this code that the second load instruction is a speculative load. Here, the value B at location specified by R2 is speculatively loaded in register R14. Here, the poison bit of R14 is turned on if terminating exception is generated by speculative load. And you can see the last instruction, which is the store instruction. Here, when non-speculative store word occurs, speculation for speculative load is raised if poison bit for R14 is on. Note here that if speculative load generates a terminating exception, then the poison bit of R14 will be turned on. And when the non-speculative store instruction occurs, it will raise an exception if the poison bit of R14 is turned on. Furthermore, to facilitate the operating system to save the user register on a contact switch if the poison bit is set, and a special instruction is included in the instruction set to set or save the state of the poison bit. So this shows that here, by using this technique, we can in fact perform the speculative exception behavior preservation, and this method is mostly used because of its simplicity and for better operation. So far, we have been talking about the first three methods. Now, let us consider the fourth method, which we mentioned earlier, known as the hardware buffering technique. If you recall from our earlier discussion on dynamic scheduling, we talked about the reorder buffer. The reorder buffer is provided and the compiler marks the instructions as speculative, and it includes an indicator of how many branches the instruction was moved speculatively, and then it also identifies what branch action, that is, whether it is branch taken or branch not taken, is assumed by the compiler. The compiler accomplished this by using either of the following two approaches. Number one, for single branch, only one bit is used to tell whether the speculated instruction has come from the branch taken or branch not taken path. This means that only one bit is taken, and if this bit is equal to 0, we can say that it gives us that the speculated instruction has come from branch taken, and if this bit is equal to 1, then it indicates that the speculated instruction has come from branch not taken path. So this single bit for a single branch, it identifies the path, whether it is a path for branch taken or it is a path for branch not taken. Alternatively, the original location of the speculative instruction is marked by a sentinel, which means whether this location has been looked out or it has been taken care of, or we can say that it has been guarded. It tells the hardware that the earlier speculative instruction is no longer speculative, so the value may be committed in the reorder buffer. The instructions marked as speculative are placed in the reorder buffer, and the reordered buffer tracks when the instructions are ready to commit and delays the write-back operation. This concept of write-back operation we have already discussed while talking about the dynamic scheduling. The speculative instructions are not allowed to commit until one of the two conditions are there, that is, either the branch have been speculatively moved and are ready to commit, or alternatively, the corresponding sentinel is reached. At this stage, we should know whether the speculated instruction should have been executed or not. If it has not been executed and it has generated terminating exception, then the program should be terminated. If not yet executed, then the exception is ignored. Now, with this much discussion regarding preserving exception behavior of speculated instructions using hardware support, let us extend our discussion on the compile time hardware support for memory reference speculation. This memory reference speculation is relatively more complex as compared to our previous discussion on the preserving speculative exceptional behavior. Here, in order to include the hardware support for memory references, we have to include some address certainty in the system. So we can say that while reducing the critical path length of the code, that is, while optimizing the code, it may be desirable to move the load instructions across the store instructions. For example, in the following code segment, you will see that if the latency of the load is high, then it may be desirable to move the load before the store instruction. Here, in order to optimize the codes with memory reference instructions, we can reduce the critical path length of the code mostly by moving the memory reference instructions with longer latency, such as the load instruction, across the instructions which has relatively lesser latency, such as the store instructions. Let us consider an example code over here and see that if the latency of the load is high, it may be desirable to move the load before the store for desirable optimization. Here you can see that the revised version of the code is shown over here on the right-hand side, vis-a-vis the original code shown on the left-hand side. Here you can see that the load has been moved before the store instruction because it has longer latency. And this simplifies the exceptional behavior, and it includes the certainty, because in this case, when the desired value from location R4 has been loaded into R3, then the add instruction will not wait for the result to be available as compared problem due to the longer latency in case of the original code. However, this optimization is not valid if the load and the store instructions are referring to the same location. For example, over here, if the contents of register R2 and register R4 are the same. Furthermore, the optimization is not valid if the compiler is not certain about this particular problem at the compile time. That is, whether the contents of the two registers are the same. This issue can be resolved by providing runtime memory address certainty. And for this purpose, two special instructions are included in the instruction set architecture. These instructions are known as we discussed earlier also, load speculatively and load verify. Here, the load speculative instruction is one which initiates a load as a normal load instruction, and a log entry is made in a table to store the memory location. Whereas the second instruction, which is load verify, is one which checks to see if the store to memory location has occurred since the load speculative instruction. If this is so, this means that if the load speculative location has already been accessed, then the new load is issued and pipeline stalls. Otherwise, it is replaced by no operation. Here you can see this thing with the help of this example code shown. The rightmost code segment shown over here it shows the use of load verify instruction, whereas the first instruction is load speculative, and it is after the verification when it decides that whether new load is to be issued or it is to be replaced by a no operation. Here, load is speculatively moved across the store, and the load verify instruction is left at the original place of the load instruction. That is, in this particular case, as you can see here, it is after the store instruction in this example. And this acts like a guardian, and it checks for the address conflict over here. When the speculated load is executed, the hardware saves the address of the accessed memory in the log table, and it finds if the subsequent store changes the location before the check instruction, that is, before the load verify instruction, then the speculation has failed, whereas if the subsequent store does not touch the location before the check instruction, that is load verify, has been executed, then the speculation is successful. Now, let us see how the speculation failure is handled. The speculation failure can be handled in one of the two ways. One method is that if the load instruction was speculated, then it is sufficient to redo the load, and this is accomplished by using the load verify instruction, which supplies the target register in addition to the memory location. Whereas the second situation may be that if the additional instruction, that is the load verify, is also speculated, then it is relatively a complex situation. Then it re-executes all the speculated instructions starting from the load using a fixing up sequence. A fixing up sequence is accomplished by using the check instruction, and that specifies the address of the fix-up code. The check instruction is basically, in this example, is the load verify instruction, and it supplies the fix-up code. Here we have discussed the use of hardware-intensive support along with the software-intensive support to achieve instruction-level parallelism. Here we observe that the improvement of code by using instructions which facilitate to move load instruction before branch, but this approach improves the execution time. However, such a transformation speculate and no improvement in the runtime is possible if the compiler mispredict the branch. This motivates us to use conditional move instructions. This conditional move instruction is used to either eliminate branches and, or we can say, or guard against the memory access violation that may terminate the program. So this means that the conditional move instruction can be used to further enhance the instruction level parallelism and still enhance the overall performance of the processor also. Now, in order to explain the use of conditional move instruction, let us reconsider the example code for two-issue superscalar which we discussed in the last lecture. This example is shown here again. Here in this example, the second load instruction after the branch depends on the prior load. Therefore, this sequence wastes a memory operation slot and incurs a data-dependent stall if branch is not taken. Here, at that time, we discussed that if the load instruction immediately following the branch is converted to predicated version of the load instruction, that is load condition instruction, move it up to the two slots and assume that the load occurs unless the third operand in this example, that is the third operand is R10, that contains a value equal to 0. Then only it improves the execution time. Here, the branch is written to skip the load instruction if R10 is equal to 0. And this instruction, that is the load word at a location R8 from the address given by the contents of R10, it is executed conditionally. This is likely to cause a protection exception which should not occur. Now, let us see how we can rewrite this program by using conditional move instruction. Here, the code should be written assuming that the loads which are no longer control dependent cannot raise an exception if they should not have been executed. This means that the branch must guard against a memory access violation. As in this example code, a violation would terminate the program. Therefore, while rewriting the program, we must consider that if the instruction load at location R8 is moved across before the branch, then the effective address must not be 0. The revised code using the conditional move is shown here. You can see that here, in order to guard the load by conditional move instruction, we need two unassigned registers. One of the register must contain a safe address for the load instruction. That is, in this particular case, we will be using register R29. And the other register must save the original content of the register R8. And in this example, we are using the register R30 for this purpose. Here you can see that in this revised code, the first conditional move instruction uses register R29. This register is unused and it contains a safe address. By moving the contents of the register R10 into this register, if R10 contains a safe address which is not equal to 0. Whereas the second conditional move instruction here shows that if R10 is equal to 0, load is incorrectly speculated, so it restores the value of R8. Now, here in this example, you have seen that the load after the branch can be speculated if we are ready to use one more conditional move instruction. And for this purpose, we will need one more unused register. However, because of this whole process, we can see that by using this conditional move instructions, we are putting lot of overhead here. Now, for this purpose, if we are ready to use the third conditional move instruction, let us use the register R31 for this purpose. The example code is rewritten and is shown here. Here you can see that the second move instruction in fact saves R9 in the unused register R31, and the load instruction before the second last conditional move instruction loads speculated, whereas the last conditional move instruction restores R9 as and when needed. Now, so far we have been talking about different techniques to preserve the exceptional behavior and to provide the hardware support for memory reference instructions and to use conditional move instructions to optimize the code. Now, with this much discussion, we conclude here our overall discussion from previous 12 or 13 lectures by saying that here we have been exploiting the instruction level parallelism using hardware and software techniques. We can say that both these approaches have certain limitations, and these limitations are as follows. Here you might have noticed this thing, that to speculate extensively, we must be able to ascertain the memory references, which is difficult to do at the compile time. Therefore, in a hardware-based scheme, such as the dynamic approaches for rescheduling, the dynamic runtime certainty of the memory address is accomplished by using the Tomasello's pipeline structure, which allows us to move load before the store at the runtime. Furthermore, the hardware-based speculation works better when control flow is unpredictable and when hardware-based branch prediction is superior to software-based branch prediction, which is done at the compile time. The hardware-based speculation maintains a completely precise exceptional model for speculated instructions. Moreover, the hardware-based speculation does not require compensation, which is needed by ambitious software-based speculation. Lastly, the compiler-based approaches have the ability to see further in the code sequence. Thus, they may provide better code scheduling than purely hardware-driven approaches. For example, the use of conditional move instructions. So with this much discussion on to what are the limitations of hardware-based and software-based approaches for instruction level parallelism, we conclude our discussion on to the instruction level parallelism here, and from next time we will inshallah take up the new topic. Thank you very much, and Allah Hafiz.